few more times, during office hours and whatnot. All right, as I said, let's get back to physics, and we're going to start thinking about molecules and atoms today, especially in terms of the electric field, and we're going to justify why the electric field is so important for atoms and molecules. Now, here's a picture of an atom of hydrogen, or a model of the hydrogen atom. Okay, one proton and an electron out here to the right. And remember, the electron is teeny. It's got about 1/2000th of the mass of the proton. So I made this proportionally smaller. So if they both had the same density, they'd have these two different relative sizes. In any case, there's an electromagnetic interaction between the two, between the electron and the proton. Here they are, just a couple arrows, same size, opposite directions, as you know from Newton's second law, or from Newton's third law, I should say. All right, so there's the force of the electron on the proton. That's this baby over here with its tail in the center of the proton. And then up here, the force of the proton on the electron. And that's the one that keeps the electron in a bound orbital state. All right. Now, the thing about electrons and atoms and molecules and stuff, usually you don't work in terms of force and newtons. I mean, it's there, and you can diagram it like this. But what we're going to try to do is get into the realm of energy and volts today, which is definitely easier and more customary for working with atoms, nuclei, and molecules. Here's water. Go ahead and draw a picture. This is a fairly precise model of a water molecule, H2O, two hydrogens, one oxygen. This one is important. So that angle between the two hydrogens, it's like 105 degrees. It's a little bit bigger than a 90-degree angle. So it's not a right angle. But it does, so it gives it kind of a V shape, and for that reason, the far end of the oxygen atom is kind of negative, because the two hydrogens, that's basically a proton with an electron, but the binding of the hydrogen to the oxygen means that the electron from the hydrogen is going to be down here, somewhere between the hydrogen and the oxygen atom. So the side of the hydrogen that faces the oxygen is going to tend to be more negative, because that's where the electron is going to be, and the proton is going to be the other direction. So the hind end of the hydrogens are both red to signify positive, and that gives it a polar structure. And that polar symmetry is reflected in that arrow with a T at the end of it. That's what we call a dipole. And that polar symmetry permits a lot of special properties for water. For instance, crystalline bonding. Okay, that happens between molecules and forms ice crystals. It also interacts between molecules in the liquid state, and that forms a little bit of cohesive force that gives us spherical droplets of water under normal atmospheric conditions, rain, in other words. So oxygen, so the electromagnetic interaction is the key to understanding this structure. Now here's another big structure, the molecule known as retinol. So just write that one down. I don't think you can diagram it, but it will be in YouTube, and you can look it up on the internet under retinol. It's the molecule in your eye, in the retina of your eye, part of the rhodopsin protein, that enables you to see. In other words, when photons of light interact with this molecule, specifically out here at the far end where that red atom is, the retinol bends, it flexes, and then it relaxes, and then it gets hit by another molecule, it bends, it flexes. And so the photons have their big kick if they're visible, if they're in the energy range Roy G. Biv. Okay. Now the retinol doesn't have a big response to infrared or ultraviolet. But in the Roy G. Biv, yes, it's the perfect energy. And this clicking back and forth, bending and relaxing, it's extremely fast. And that is what activates the optic nerve that transmits signals into your brain, which you then form into a perception known as vision, color vision. Right? And it's the rhodopsin protein, and the retinol molecule in that protein is the actual thing that does where the work is done, I should say. It doesn't do the work, it's where the work is done. So there's all kinds of molecules that are of interest, and forget about DNA. That's this enormous molecule. You know, thousands and thousands of atoms bonded together, and so it's a lot of stuff to learn about. Now, before we go into molecules, which is basically our topic next week, molecules in the periodic table, let's go and make a comparison of gravity and electricity. You know, they're both inverse r squared forces. They're all something divided by r squared as to strength. So a neutral hydrogen atom has one proton, one electron, as you know, and they're bound by the Coulomb interaction. It's attractive. And this sketch is this more of an idealized sketch where the two particles look the same size. They are not. Now, gravitationally, you know, they both have the same color. In other words, they have the same amount of, or they have a different amount of mass, but it's always attractive. Now, as far as the neutral hydrogen goes, in the lowest energy state, in other words, the smallest state where the electron is as close to the nucleus as it can get, that's what we call the Bohr radius, after a scientist named Niels Bohr, B-O-H-R, from Denmark. That's at about 0.05 nanometers. Okay, that's about 5 times 10 to the minus 11 meters. Okay, and that's based on some of the observations we can make macroscopically about hydrogen. You know, hydrogen produces a beautiful spectrum, which we'll try to view next week here in the lecture hall. Did we do that already on the first day of lecture? Hydrogen spectrum? Did we look at that through diffraction gradients? Must not have. We'll do it next week. I sometimes do it the first week, sometimes I do it the last week. Now, the proton and electron interact gravitationally. Each one has a little bit of mass. Sean?
0.05, is that a constant?
Actually, it is the Bohr radius is considered a constant of nature. Yeah, it's got a bunch. It's got like the mass of the electron, the charge of the electron. It's a big combination of other fundamental constants. So yes. All right. So the Bohr radius, half a nanometer, or 0.05 nanometers. You know, that's considered your basic unit when you're thinking about the sizes of atoms. You know, how many Bohr radii is it? And if it's got more than one, you know, then you say, all right, it's kind of big. If it's smaller than that, it's kind of small. So like chlorine atoms are pretty small, and you know, different atoms, you know, depending on how many electrons they got, are bigger or smaller. So yeah, Bohr radius is considered a constant of nature. All right, now electromagnetically, each has electric charge. So it's logical to ask yourself this question. You know, which interaction is stronger? I mean, they've got a gravitational interaction because they both have some grams of mass, a little teeny tiny fraction of a gram. And they each have an electric charge, plus or minus one fundamental charge, symbolized E. So what we're going to do is make this humongous calculation now, and I'm going to do it on the screen. We're going to compare the force of gravity to the force of electricity in the hydrogen atom. And we're going to do it on the screen. Go ahead and jot down the specs. You already have them, basically. The mass and this is the first time I've given you the mass of the electron and the mass of the proton. The size ratio is 1 to 1 in the charge column, but in the mass column, it's 1 to 1837, or roughly 1 over 2,000, 1 to 2,000. All right. So go ahead and jot those down, and we're going to put those into, the force law, GM1 M2 over R squared. All right, and we'll use R squared, the Bohr radius. And then we're going to put KQ1 Q2 over R squared for the electrical force. And then we're going to compare the two forces. All right. Now this table of information, the charge column, that's plus or minus 1.60 times 10 to the minus 19 coulombs. And we're going to deal with this in a manner that is highly righteous. All right, now I'm going to go to the next page. If you didn't have all this stuff down, you can look it up on the internet easy. And of course, it'll be on the YouTube. All right, so here we go. Coulomb interaction in the upper left, gravitational interaction modeled in the lower right. Now, the mass goes by volume usually. So 1,837 times more volume means that the radius is going to be 1 to 12.25. So what that means is 12.25 to the third power is approximately 1,837. All right, if you don't believe me, just type it in on your calculator and you'll see. So if we were going to represent the proton and the electron by relative volumes, it would, as I've shown you before a few slides ago, it would look about like this. All right, so we're not going to do that. If you go by charge, they're equal, plus or minus 1 fundamental charge. So the red and the blue spheres are kosher to call them. It's kosher to call them the same size. Gravitationally, with mass, to be truly in proportion, it would look like this. But we're still going to go with this diagram down here, and then we're going to let the numbers do the talking because we're going to do a big, ginormous calculation. Okay, now the next slide, I want you to look at it, okay? But I don't want you to write it down. If you want to write it down, you can do it from YouTube. All right, so the writing this down is not what I want you to be able to do. I'm going to write down GM1 M2 over R squared, and then KQ1 Q2 over R squared. Here we go. There they are. All right, so GM, mass of the proton, mass of the electron over R squared. And I haven't, Sean, I didn't put in the Bohr radius there. I just put R. But whatever the radius is, they're gonna, if they're 2 miles away, this is gonna be the force for it. If you have 2 miles down there in the denominator. Okay, so 6.67 times 10 to the minus 11 Newton per meter squared, or Newton meter squared per kilogram. That's the capital G. And then 1.67 times 10 to the minus 27 kilograms. That's the mass of the proton. And then smaller than that, 9.11 times 10 to the minus 31 kilograms, mass of the electron. Now you can see that we're going to have to deal with some scientific notation here. All right, now don't worry about writing this down unless you feel really strong, because it's pretty nasty, to tell you the truth. All right. Now down here in the bottom equation block, KQ times the K times Q of the proton times charge of the electron, and you can, and divided by R squared. So K is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. All right, so that's the that's Coulomb's constant, we call that. And 1.60 times 10 to the 19 minus 19 coulombs, that's the mass, or excuse me, that's the charge of the proton. And then negative 1.60 times 10 to the minus 19 coulombs, that's the charge on the electron. Now, the thing about this is it is nasty. It's bodacious. There's scientific notation at the wazoo. And, calculating a number of joules here is going to be a pain in the gluteus maximus. But there is one thing that we can do, and because we're going to make a ratio of these two babies. So we're going to take the ratio FG over FE. And because that is the case, we can cancel R squared top and bottom. All right, so just burn those babies out. Because we're about to go with this ratio. And that ratio is going to be fairly nice. All right. Because basically now all we have to do is the numerator of the top equation block divided by the numerator of the bottom equation block. All right. Now don't worry about writing all this down. Here it is. All right. All right. There's the ratio. All right. Now I want you to look at that. And just remember that, you don't have to calculate that. But I'm going to calculate it for you. All right. So look at the scientific notation. You got 10 on top, 10 to the 9, 10 to the minus 19, 10 to the minus 19 again. So that's 10 to the minus 29 on top. All right. And then down on the bottom, you got a lot. Minus 11, 10 to the minus 27, so that's minus 38. And then 10 to the minus 31, so that's like 38 and 31 is 69. So you got 10 to the minus 39 down there in the bottom. And that's because gravity is such a small force, right? Which is what we're trying to prove here. All right, so if you calculate, so there's the top again, what I just had on the previous slide. If you stream out the scientific notation, you have 10 to the minus 29 newtons on top, and you have 10 to the minus 69 newtons on the bottom. And then you have the numeric part. Now this part's fairly easy. And you can verify me on this. 8.99 times 1.6 times negative 1.6. Go ahead and verify me. That's negative 23 approximately. Anybody verify? You got it? Who verifies? 23. Go ahead and check it. This part's not hard, just the numeric part. Anybody verify? Raise your hand when you verify. 8.99. Okay, got it. Good. All right. Anybody else? Trying to verify? I got you, Daniel. Okay. Well, let's keep going. The denominator, similarly, we got that. There's nothing to do about that 10 to the minus 69, although we're going to put it up on top eventually here. But the numeric part, 6.67, 1.67, 9.11. So verify that. That should come out to 101 approximately. All right. So anybody verify 101 on that one? You got it? Okay. All right. Anybody over on the left? Got a 101. You got it? Okay. Anybody over on the right? We got to have bilateral and center. So anybody on the right? Are you okay? Got it. All right. 101. All right. So now here's what I did. I mean, I just parked the 8.99 there. I parked the 1.60 right here. Okay. And then the negative 1.60 I parked right there. And then I put all the scientific, the exponents over there in 10 to the minus 29. And then the numerator, I did the same thing. So my 6.67 is down here. And my 1.67 is right here. And my 9.11 for the electron is right here. And I have my 10 to the minus 69. Now we can deal with those powers of 10. 10 to the minus 69 in the denominator is same as 10 to the regular 69 in the numerator. So this is equivalent to 10 to the minus 29 times 10 to the positive 69, right, in the numerator. And that means that your scientific notation over here is 10 to the 40, all right? And that, my wonderful students, is the moral of this calculation. So go ahead and write down 23, and you could ditch the minus sign now. We don't really care about the signs of the forces. We're just talking about the magnitudes. So you got something times 10 to the 40. It's basically 0.2 something times 10 to the 40. So this strength ratio between the electric and the gravitational force is 10 to the 40. So what that means is that the strength of the electric interaction is roughly 10 to the 40, that's a 1 with 40 zeros, times bigger than the gravitational force. Now, here's the bottom line for this analysis. It is for this reason that we consider atoms to be electrical and we do not mess around with the gravitational. It's there, but it's so small, 10 to the 40 times smaller than the electrical that Raven, we're just going to go with electrical in the atom. And then when we do the nucleus, there's two forces even stronger in the nucleus, all right? Or one really strong in the nucleus and one a little bit weaker. But for us, when you're thinking about atoms and molecules, don't worry about gravity, all right? Now, the thing about gravity is always attractive. Electricity is positive or negative, and electrical forces can be screened. But you can never screen gravitational forces, and that is why the universe on the large scale is governed by this extremely weak force. Okay, and it's kind of weird how that happens. The biggest scale of all, the weakest force controls it, because everything else is approximately electrical neutral. When you're far, far away from a galaxy, that galaxy is roughly electrically neutral. Same number of protons and electrons over there, all right? But on the gravitational scale, it's got a lot of mass, and so that's what governs this on the scale of stars and galaxies and planets. All right, now, as I said, you're not going to have to do that calculation, but I do want you to remember 10 to the 40. And the vocabulary term that attaches to that is ginormulous. Okay, it's beyond big. It's ginormulous. Now, let's keep going, and we're going to talk some more about energy levels, and we're going to talk about field lines. And if you've ever done this, science experiment like in 5th grade or middle school, you take a bar magnet and a piece of paper and you sprinkle some little tiny iron filings onto the paper, and they make it form into this cool pattern, where the electric field lines are, the filings are all lined up with the magnetic field. Those are field lines, or that's a representation of field lines. And electric fields have field lines as well. Now, here's a negatively charged metal sphere. So the way that you would write the field lines, they don't have, they don't look like a bar magnet. They just go straight inward. And the rule is that if there's some hypothetical positive charge outside the negative sphere, it would be attracted. And therefore, it would go inward, and that is the direction of the field lines. If you have some arrangement of charge, okay, Nina, that, whatever it is, you ask yourself, well, what does a hypothetical positive test charge do? And in this case, it would want to move inward, radially inward, if you just park it out there, right? And so even for if you had a positively charged sphere, with a bunch of extra protons in there, then the field lines would go outward because the red test charge would be repelled. Okay, right? So field lines. So for a simple electron, the field lines are directed inward. For a simple proton, the field lines are directed outward. However, an atom of hydrogen is an electron and a proton bound together. So how does that look? Well, this is what it looks like. It's called an electric dipole. Okay, a positive and a negative fairly close together. Now these arrows represent forces, but the field lines, basically follow those same directions. And you can notice that this dipole field is symmetric left to right, kind of, and it's symmetric top to bottom, top and bottom. So the upper half, so like right here, up here, This arrow up here in the middle and above is leftward, and so is this one down here at the very bottom in the middle. It's also leftward. Now this arrow over here to the upper left of the electron is aimed, it's a certain size, and it's aimed downward and in. The corresponding arrow over here to the upper right of the proton is aimed away, up and to the right, but it's the same size, all right, because the electric charges are the same size, all right. So that's called the dipole field. Here's another look at it. These are the field lines. It's basically connecting up all those arrows just in one swinging line. And this is actually what a magnetic field line looks like as well. And that is not coincidental, because the magnet is made up of electrons and protons and neutrons, and they cast a very particular electric field. They're all in motion, and when you put them in motion, you get a magnetic field that looks like this. So there's your dipole field. And a water molecule has now got to adapt another minus charge in there. All right, and that breaks up the dipole symmetry. But you still have some symmetry, which we mentioned earlier. Okay, and but this is the dipole field. Also notice that right down the middle, if you draw a symmetry line straight down the middle, vertically and right through the halfway point between the positive and negative, that's a symmetry line, all right? And the field lines are perpendicular to that symmetry line right at that point only, all right? There's another symmetry line. You can't really make it out too well here, but horizontally, the horizontal axis between the two positive and negative charges, that would be another symmetry line for the dipole field. All right, and we'll have some homework coming up to give you a little bit more thinking about the dipole field. It's pretty important. Now, let's talk about a positively charged sphere. Now, the Van de Graaff generator is this. Actually, the Van de Graaff generator is, let me go back here, that's the Van de Graaff generator. It's the thing where you go to the science fair or something, and I'll try to bring it in next week, and you put your hands on it and you turn it on, and it develops a lot of static electricity. And if you're it wouldn't work for me because my hair is so short, but if you have longer hair like this young lady, the positive charge will go from the sphere into her body, and it'll accumulate in her extremities, which in this case her hair, and it'll fly out into the universe like this. Okay, now this is not at UCF, but the one that I just showed you is. So let's go through here and get back to that. All right, now this is one of my students from, see that lecture hall? Does that look familiar? See the tiles behind it? Like these ones right over here. Okay, so that's one of my guys from a few semesters ago, and there's the Van de Graaff, and you can see his hair is flying into the universe. So this student's in contact with a positively charged Van de Graaff generator, and its field lines move radially outward, and that's what a small positive test charge would do. Okay, so here's a diagram of that. A positive test charge would move outward. So here's go ahead and check out my cool animation. Ding. That's what my animation does. Okay, so the positive test charge would move outward. So what that means is your high potential energy is near the proton, or near the positively charged sphere. All right. So higher EPE, electrical potential energy, is close to the sphere. So like this inner dashed line right here. Okay, so that would be higher electrical potential energy, and outside, this outer dashed line would be lower potential energy. all right? Higher kinetic energy, all right? But now if you think about what a small negative charge would do, so here's my small negative charge out here, starting out to the right, and where the EPE is low for the proton, the EPE is high for the electric charge, because the electric charge is going to be drawn inward. It's going to want to accelerate toward the positive, all right? Because it's a negative, it wants to go towards the positive. So what that means is that the higher EPE is far away from the sphere if you're an electron, all right? And it's so higher EPE is far away from the sphere. So that means that this outer dashed line is high EPE for the electron, and the inner dashed line is lower EPE for the electron. Now that's a problem. You know, when we're talking gravity, one potential energy is good for everything. You know, like minus mg delta y. That works for anything. Doesn't matter what you got. But for electrical, what the positives do is the opposite of what the negatives do. So you got a little bit of confusion. It's only two different states. But so what scientists have done over the past few centuries is use something called volts, a voltage. And the fancy name for it is electrostatic potential. And not electrostatic potential energy, electrostatic potential. And the units that we measured in is volts. So go ahead and write down that vocabulary term, electrostatic potential, i.e. voltage. And we use that as an abstraction of potential energy. And the reason is that there's a plus or minus. So what we do is we extract out the charge. So we divide the potential energy by, or the joules by a Coulomb, and then we work with that. So here's the definition. We use the electrical potential energy of the proton. We divide it by the number of coulombs in the proton, and that's the number of volts. So that we consider the volts to be high near the sphere and lower as you move away. Now it's an abstraction of joules of potential energy, all right? But using this concept of volts, we can use a voltage to really do what we want in terms of atoms and molecules. And, you know, we use voltages for everything, you know. Did you know that on your battery, if you look at your battery, one end is plus, one end is minus. The things that move in a battery or in a circuit, a normal circuit anyways, you know, household circuit, it's the electrons. The electrons move because they're so much smaller mass. They're easier to move, okay? It's like when you're moving furniture, what do you move first? Well, you move the small stuff, the boxes, you know, and the end tables and stuff, and then you get to the sofas. That's where you call me in and I help move. So before I moved to Orlando, I was, you know, like when I was in grad school, I had to always I would always get roped into helping friends move, you know, or, you know, they have to move a dishwasher or, you know, washer and dryer up and down the stairs. They always called me and my buddies. Anyways, so so voltage is high near the sphere, lower as you move away, in accordance to what the positive test charge. So all this is oriented to the positive test charge. But of course, whatever the positive test charge does, the electron does the opposite. So that's good, right? So we're using this abstraction. And what we say is that the protons drop, everything drops to lower potential energy. But if you're talking in terms of voltage, protons drop to lower voltage zones, you know, wherever they happen to be, right? So far away from a sphere. But if you have a pair of plates, you know, like inside of a battery, you know, you have a different distribution of volts. But protons will always drop to lower volts. But you know what we say for electrons? They drop, so to speak, to higher voltage. So electrons consider that to be their downhill. Voltage to an electron is something that they automatically, it's like anti-gravity. They go up in voltage. They like to go up in voltage. But that's really down in potential energy, but up in voltage. So basically the charge times the voltage is a unit of energy. All right? And so because the voltage is basically a certain number of joules divided by a charge. So charge times the voltage is equal to energy. All right? Now, a Coulomb times a volt, this is basically the definition of a volt. A Coulomb times a volt is 1 joule. And that's good for everyday scale of circuits in your house. And millivolts for, things that you're operating, microvolts inside of your phones and stuff, millivolts. And, for the big transmission lines, they're hundreds and thousands of volts. And we transform the voltages down to household 110 volts, I think it is. But a fundamental charge E times 1 volt is considered an electron volt. And that is a unit of energy. And it is actually the best energy unit for atoms and molecules. Because the charges in atoms and molecules that you're worrying about are protons and electrons. And those are, protons are E and electrons are minus E. All right? So a volt times an E, a volt times a minus E is a plus or minus electron volt. All right? So 1 electron volt, hopefully this makes sense to you, it's equal to 1.602 times 10 to the minus 19 joules. Now we're going to be working with atoms and stuff, so we're going to be working in electron volts, but you can convert it with this formula into joules whenever you feel like it. All right? Question? All of it. We're going to have new information on Tuesday and some more new information. We're going to wrap things up on Thursday, and then we'll have the review. Yeah. So maybe an hour new information on Thursday, followed by the review set. So yeah, we still got a little bit of stuff because I didn't want to put the last midterm during the last week of school. Okay, now hydrogen. If you've ever seen a neon light, that you see at a store, where it says open or something like that. It's a vacuum tube that's filled with a little bit of neon. And if you go up to near the sign, if you're inside the store where the sign actually is, and you walk up near the sign, you can hear it buzzing. That's the transformer. Because what they're doing is they're zapping the neon in the tube with some high voltage. Not a whole lot of current, but a whole lot of voltage. And when they do that, it will glow. And it will glow with very specific colors. Now, neon has a reddish orange color. Hydrogen has a set of colors. It has a big, bright red line. It has an aqua colored line. And it has 2 purpley blue colors that it emits. And so the mixture of all those is kind of pinkish red for hydrogen, right? And that's what's known as the spectrum of hydrogen. Now we'll try to look at that next week. I'll try to get those in all the way over from the mathematical sciences building and get that stuff over here for you to actually eyeball that stuff. Now by observing that, we know that pure hydrogen produces a specific set of colors. Not all the colors of the rainbow, I just mentioned them. The red, the aqua, and the 2 purpley blues. All right. So it must be true that the electron lives at only certain specific and countable orbits. And that's because when the electron drops from a lower orbit to from a higher orbit to a lower orbit, it emits a photon of light. All right, and that's the quantum principles. That orbits can be numbered, and we know that they're numbered because not all colors of the rainbow are permitted. There's only certain amounts of energy and therefore certain amounts of wavelength certain amounts of color or certain types of colors that the hydrogen atom permits, or I should say emits. Okay? So now EPE is the energy of position. So EPE is also restricted to a certain value, and we say that energy is quantized. So the orbits are quantized to a certain distance. And Sean, the inner distance for hydrogen is the Bohr radius. All right. Now the outer orbits, we've got 3 outer orbits here, and they're multiples of the Bohr radius. They correspond to let's see, that corresponds to lower voltage, and for the electron, uh, higher potential energy out there. So electrons drop or gain precise amounts of delta E. So when they drop, delta E is negative, and all that energy, Carlton, goes into the energy of the outgoing photon. If it absorbs a photon of light, like what retinol does, if hydrogen absorbs a photon of light of just the right color, it will boost it up to one of the upper energy levels. So the energy levels start deep in the negatives, and then they increase. So for n equals 1, that's the innermost orbit, the potential energy is negative 13.6 electron volts. The next one up, negative 3.4. Go ahead and write these down. These are very important energies. The third, negative 1.5 electron volts. And the fourth one that I've got here, negative 0.9 electron volts. So you can see that they're getting closer to 0, but what I said was correct. It's a larger potential energy as you go away. All right? And so electrons want to fall towards the proton. And you can keep numbering them. Now, the largest, if you just keep going up, higher and higher energy levels, the energy approaches 0. All right, so they get closer and closer to 0. And these ones, you can see the jumps are not, we can measure these jumps. The way that we measure the jumps is by measuring the color and then figuring out the frequency of the photon that's emitted, and that tells us the energy. So the binding energy of the ground state of the electron is 13. So we would say the binding energy is 13.6 electron volts. In other words, that's how deep it is below 0. And we got to blaze it. If we want that electron to be ionized, if we want to eject that photon, that electron, we got to blaze it up with something that's negative 13.6 electron volts of energy. So just the right flavor of photon will blaze that thing outward and ionize the atom and separate the electron from the proton. So the first excited state, that's what we call n equals 2, 3.4 electron volts. So you don't need as much energy to blaze out an electron that's out there in the n equals 2 energy level. Okay, and so on and so forth. And what this means for hydrogen, it also means for other atoms. For instance, sodium, Na, has an outer electron that's really, really weakly bound. And so it's easy to get ejected, it's easy to get ionized, and it's easy to be stolen by another atom. If you bring another atom close to sodium, like if you bring chlorine in close to sodium, the chlorine will steal that outer sodium electron, and it'll form a sodium ion that's positive and a chlorine ion that's negative. And guess what happens? You have an ionic substance called salt, NaCl. Okay, and that's one of the things that we're going to talk about with the periodic table next week. Now, I have a homework assignment that I think is going to fit everybody's objective for this weekend. So let's take a look at that right now. No homework. You're dismissed. If you want to get your Scantron printout, come on up and I'll dig it out of the pile. Otherwise, you're dismissed. I'll see you next time.